What kind of pan will you use to fry a steak? Maybe a heavy old cast iron skillet? Or maybe a light aluminum non-stick pan? Well, your choice is up to you. Cast iron is the right answer, but these pans will behave very differently to each other for a very particular reason: heat capacity. Esto es Real Chem. Proportional reasoning is one of the most powerful ideas in science and math. When it started to make sense to me as a student, it actually opened up a whole new world, because so many algebraic equations we use in science are based on these proportional relationships. Suddenly, everything started to make sense. So, how do we use it to understand a quantity that is proportional to more than one other quantity? Like what we need to do to understand heat capacity. Exploremos. The heat capacity of an object is how much energy it takes to raise the temperature of that object. It takes about 0.4 joules of energy to heat a gram of one block of copper by 1 degree Celsius. If we double the mass of the block to 2 grams, the heat required doubles to 0.8 joules. So heat, Q, is proportional to the mass of the block, M. If we wanted to heat 1 gram block by 2 degrees instead of 1 degree, it would also take twice as much heat. So heat, Q, is also proportional to the change in temperature. If a quantity is proportional to two different quantities, it is also proportional to the product of those quantities. We can convert this into an equality by introducing a proportionality constant. We call this proportionality constant C, the specific heat capacity, and it depends on the substance we are heating. The heat capacity of copper is 0.385 joules per degree, meaning 0.385 joules are required to heat 1 gram of copper by 1 degree. The heat capacity also applies to cooling. When a gram of copper is cooled down by 1 degree, it gives off 0.385 joules of energy. Why is it reasonable to call this proportionality constant the heat capacity? Suppose I wanted to use a metal bar to move energy from a beaker of boiling water to a beaker with room temperature water. I put the bar in the boiling water, and heat is transferred from the water in the bar to raise the temperature to 100 degrees. Then I put the bar into the cool water, and the heat is transferred until the bar and the water reach the same temperature. For a copper bar, the water is heated by about 4 degrees. If I replace the copper bar with, for example, silicon bar, the water is heated by about 8 degrees. Silicon transfers twice as much energy as the copper. This is because the heat capacity of silicon is about twice that of the copper. It takes twice as much energy to heat the silicon bar as it does to heat the copper bar. And when cooling, the silicon bar releases twice as much heat as the copper bar. If we view the bar as a bucket we are using to move energy from the hot to the cold water, the capacity of this bucket is twice as big for silicon versus copper. So the term heat capacity of a substance does actually make sense. A large heat capacity means it takes more energy to heat the substance. So the substance has a higher capacity to hold the energy being transferred through heat. Heat capacity is relevant when selecting a pan for certain cooking tasks. A heavy cast iron pan takes a lot of heat to get a temperature, but its temperature is stable because it has such a large heat capacity. Next time you're in the kitchen, remember that cooking is chemistry and that your choice of pen matters. Así que elige con cuidado. So explore and remember to have fun.